Chapter 6: AI-powered process and equipment enhancement across the industrial world. Part 2: Smart technology-driven resources and manufacturing. The resources industries, such as minerals, metals, and mining, as well as the manufacturing sector, have seen a wide variety of impactful AI use cases over the years, many of them which I have experienced firsthand. Current economic realities mandate getting the most from existing assets, and this is especially relevant in the capital-intensive industries such as mining and manufacturing, where doing things the way they have always been done is no longer an option. Even minor improvements in production performance can make significant contributions to the bottom line, leading engineers to critically review the processes in their charge. But this can be a daunting and difficult task without the proper smart technology and tools, because the processes that are most in need of improvement and that will yield the most profitable results are usually those that are too complex to optimize manually, such as metal beneficiation. Over the last few decades, we have seen a significant increase in instrumentation and digitization across mining and manufacturing plants, with more sensors and IoT devices, along with industrial application layer applications such as programmable logic control systems, supervisory control and data acquisition systems, distributed control systems, manufacturing execution systems, maintenance systems, and enterprise resource planning systems. AI solutions capitalizing on all available structured and unstructured data can help to enhance every application across the industrial application spectrum. In the minerals, metals, and mining industries, we have especially seen AI being applied to the control and human-computer interface layers for smart control applications to enhance the standard PID control and improve support for operators, process engineers, and production managers to better understand process and equipment behavior and help to troubleshoot and optimize their plant. To do this successfully, the first step is to thoroughly understand the process being addressed through modeling and simulation using historical data. The second is the implementation of AI-driven solutions that address the identified problem in real time. Then comes the distribution of information in a form that is relevant to the people that must use it to make informed decisions. The information needs of management, process engineers, maintenance staff, automation personnel, and operators, for example, are all different. Lastly, to be a long-term success, any process improvement program must include sustained skills transfer, engineering assistance, training, and effective rollout schedules, as well as ongoing assessment of the business value of the improvement. So, process performance enhancement involves more than just AI or software. It is all about the tools, the solutions, and the program to bring it all together. Some relevant use cases for deploying AI solutions in the resources and mining sector include seismic data analysis, rapid process and equipment troubleshooting, real-time process and equipment monitoring, diagnostics and anomaly detection, predictive maintenance, advanced process control, and overall process performance enhancement. We have seen the same on the manufacturing side, although the automotive and assembly sectors have shown higher AI adoption and digitization compared to, for example, consumer packaged goods, and even building materials and construction, which has been very low. Manufacturers are focused on improving product design yield and efficiency, optimize pricing, refine sales leads prioritization, automate supplier assessment, anticipate parts requirements, reduce material delivery time, improve processes by the task, automate assembly lines, reduce errors, limit product rework, optimize flight planning and route and fleet allocation, enhance equipment maintenance engineering and training, and predict sales of maintenance services. AI can help to enhance each of these application areas. Some relevant use cases for deploying AI solutions in manufacturing sector includes real-time, batch, and discrete process monitoring and diagnostics, rapid process and manufacturing equipment troubleshooting, intelligent process control, optimizing supply chains and creating greater economies of scale, improving preventative maintenance, achieve better repair, maintenance, and overall performance with greater predictive accuracy to the component and part level, increasing production yields by the optimization of the team, machine, supplier, and customer requirements, providing more relevant data so finance, operations, and supply chain teams can better manage factory and demand side constraints, knowing the right price to charge a given customer at the right time to get the most margin and closed sale. Better machine sensors can lead to safer workplaces. Manufacturing as a service with AI enabling subscription models for production service. The use of intelligent virtual assistants and advisors, and Uber maintenance. Apart from all these generic manufacturing-related use cases, AI in the automotive industry is also helping to pave the way for autonomous vehicles, where they are seen as a post-Uber disruption to public and goods transportation. As we have seen with Tesla, Waymo, and others, machine learning-based pattern recognition gives these vehicles the ability to identify their surroundings and to take actions in any given scenario at various levels of autonomy. This is done by feeding state-of-the-art AI systems with real-time data from sensors, cameras, GPS, LiDAR, and cloud services to produce control signals that are used to operate the vehicle. Apart from helping to ensure proper and safe driving by, for example, enabling emergency control of the vehicle, active monitoring of blind spots, and cross-traffic detection, it can also be used to monitor and learn driver and user behavior, predict and prescribe preferences based on user behavior, offer predictive and prescriptive maintenance of individual vehicles as data about the physical condition of the vehicle is stored in the cloud, and provide accurate data feeds for regulators with respect to traffic violations and insurance companies for driver risk assessment and to streamline the handling of claims. We also see AI-driven robotics use cases in manufacturing with industrial robots that can do tasks with high speed, accuracy, and endurance, such as those in material handling, assembling, disassembling, welding, painting, dispensing, packing, labeling, inspecting, and testing. In the future, one might expect spectacular applications of AI and robotics in the resources and manufacturing industries that can include the use of dynamic, highly mobile robots, such as those being developed by Boston Dynamics in the form of Atlas, Handle, Pick, and Spot. Given the continued expansion of the global economy and the rise of living standards, the Organization for Economic Cooperation and Development has projected in their Global Materials Resources Outlook that the world's consumption of raw material is set to effectively double from approximately 90 gigatons today to 167 gigatons in 2060. Over the next few years, the global smart mining market size is expected to reach $24 billion in 2027 from approximately $9.3 billion in 2019, which implies a compound annual growth rate of 13% from 2020 to 2027. Smart mining can be described as a process that uses data, information, technology such as AI and other state-of-the-art software solutions, and autonomy to gain better productivity, reduce operational costs, and enhance safety for a mine site. These smart technology-driven solutions also comprise remote-controlled robotic equipment for mineral and metal extraction to help decrease the danger for miners. With the manufacturing sector accounting for almost 16% of the global GDP in 2018, it is clearly also a major part of the world economy and one of the key reasons governments across the globe is promoting the manufacturing sector, such as Make in India and Made in China. As an example, China wants to transform itself into a leading manufacturing power that moves up the manufacturing value chain by utilizing innovative manufacturing technologies or smart manufacturing, whereas India wants to reduce their dependence on exporting nations by producing goods in their own country, supporting by significant foreign direct investment. However, with the outbreak of the COVID-19 pandemic, we have seen a significant decline in the global foreign direct investment. The United Nations Conference on Trade and Development has estimated that COVID-19 could cause global foreign direct investment to shrink by 5 to 15% due to the downfall in the manufacturing sector, along with the factory shutdown with substantial negative impacts in the energy, chemicals, electronics, airlines, and automotive sectors, and a shortage in raw materials. Despite this knock on the manufacturing industry, the global application of AI in the manufacturing market is expected to still grow strongly with a compound annual growth rate of about 55% until 2025, when its size is projected to be approximately $15 billion. With radical shifts in demand and the increasing use of AI and other smart technology solutions, manufacturers are experiencing a growing disruption of the entire end-to-end value chain and forcing them to brainstorm new supply chain models, adopt new plant designs, and redefine their manufacturing footprints. Process manufacturing in industries such as minerals, metals and mining, oil and gas, pulp and paper, refining, cement and glass, chemicals, electric power generation, food and beverage, life sciences, as well as water and wastewater, typically utilizes physical, chemical, and compositional changes via continuous and/or batch processes to convert raw material or feedstock into a product. A subset of these industries, such as life sciences, minerals, metals and mining, and fine chemicals, include a mixture of continuous, sequential or batch, and discrete processes that are often referred to as hybrid applications and industries. AI-driven process performance enhancement can be applied to continuous, batch, or discrete processes, as well as hybrids thereof. A continuous process is defined as the continuous flow of material through various processing equipment. Once a continuous process is operating in a steady state, the goal is to produce a consistent product at optimal yield levels. Continuous process manufacturing includes industries such as refining, chemical, petrochemical, and oil and gas applications, and differs from discrete and batch processes in manufacturing with respect to its non-stop operation, unscheduled downtime, high asset value, capacity utilization, and cost. In contrast, the nature of batch process manufacturing is typically shift-orientated, with a low-volume, high-value focus, more agile, rapid response to market demand, and high regulatory content. In general, a batch process is defined as a process that leads to the production of finite quantities of material by subjecting quantities of input materials to an ordered set of processing activities over a finite period of time using one or more pieces of equipment. Some examples of batch processes are biotech product manufacturing, pharmaceutical formulations, soap manufacturing, dairy processing, food processing, and beverage processing. Discrete process manufacturing includes vertical markets such as industrial manufacturing, high technology, automotive, aerospace, defense, machinery, and electronics, and produce items such as cars, airplanes, consumer electronics, computers and accessories, appliances, and other household items. A discrete process involves the production of things, where a part or a specific quantity of parts in a group moves from one workstation to another, gaining value at each location as work is performed. In a discrete process, each thing or part maintains its unique identity. Process and equipment performance enhancement for the manufacturing and resources industries is about operationalizing end-to-end integrated AI-based solutions that deliver process and equipment troubleshooting, monitoring and optimization using all available structured and unstructured data. Rapid process or equipment troubleshooting involves identifying and understanding causes of variation in key performance indicators such as throughput, quality, and yield, or key production, process, or equipment-related variables. To extract knowledge from process or equipment models, causal and sensitivity analysis is typically done on machine learning-based AI models that are trained on data to be representative of specific process or equipment behavior. Further insights can be extracted by using these AI models in what-if scenario analysis and benefit estimation simulations. These models can then also be used in real-time or batch fashion in monitoring and diagnostic solutions that feed off real-time or batch data. Other real-time applications include predicting lab measurements via software sensors for use in process control applications, AI-driven advanced process control, and setpoint optimization. Machine learning can also be applied in safety and security-related applications for identifying and tracking people in the work environment and detecting anomalous behavior. Other applications include smart sensors that use machine learning for pattern recognition on video and audio feeds, which can complement the traditional sensors used to control processes and equipment. Some of the most impactful use cases for process and equipment performance enhancement that I have personally been involved with via my AI company Season Systems as well as Cortex Logic more recently include the stabilizing of the feed rate in a grinding process that led to a 5% increase in throughput for the mining company. In an equipment-related performance enhancement use case, the availability of haul trucks was increased from 70% to 85% using predictive analytics that focused on the engine, transmission, and braking characteristics of the haul trucks. In another equipment-related use case, the Cortex AI engine was used at a major diamond producer to increase throughput, yield, and reduce equipment risk through improved decision-making and automating mining operations. To not have operational mining equipment available has a significant impact on revenue and operational costs. In this particular use case, a data mining solution helped to gain insights with respect to how geological features and diamond yield correlates during sampling. A machine learning-based solution was then developed that, amongst others, maps hydrophone signals to geology in order to create signals that are used for improved predictive maintenance of key operational mining equipment and automated mining tools. Another AI use case for this diamond producer involved the use of machine learning-based models to predict forward demand for diamonds and related categories across market, product category, and price category. This allows for optimization of diamond sales and the supply of rough stones to manufacturers and price it accordingly to meet demand. Our AI-enabled process troubleshooting and advanced process control solutions implemented via the CSIN software at a steel rolling plant in South Africa resulted in business value of at least $1 million per annum by a reduction in the plant's project cycle times, real-time identification of process set points, and a better understanding of the process through data-driven insights. At a mineral sands plant in Western Australia, a machine learning-based solution was used to solve a 3-month kiln grade problem by identifying the causes for lack of proper grade within a week and help to increase the grade with a few percentage points. With the AI-driven CSense software, a remarkable contribution has been made towards increased operating ratios at a major aluminium paste plant in South Africa, where the plant's waste production rates has been significantly reduced. Process transparency and knowledge has been increased, and the overall process variation throughout the plant has been reduced to provide high throughput of good consistent quality anodes for an efficient alumina reduction process downstream to produce aluminium. The software was also used at a zinc plant where AI solutions that connected to all process, analytical, and operational data helped to accurately predict the root causes of process variation in a range of operational processes. The efficiency of one of the world's largest primary platinum producers in South Africa was also improved by an advanced process control solution that helped to maximize production through the intelligent control of complex processes. At the platinum smelter, 2 conflicting processes were also successfully integrated without spending capital or changing the plant in any way. An AI-based metal accounting solution that reliably provides a real-time estimate of all metals in process each stage of the production value chain was also implemented at the same platinum plant where validated information was generated from the bottom layers that includes sensors and control systems for the manufacturing execution systems and the enterprise resource planning applications. At a base metal refinery plant, an intelligent advanced pH controller was implemented that helped to reduce the pH variation in a leaching process by 40%, with significant increases in nickel and iron extraction efficiency, as well as the grade of the platinum group metals. Advanced process control solutions were also implemented at one of the world's largest copper and gold mining plants that lead to significant increases in feed rate of up to 15%, implying an increase of 15 tons per hour. AI-driven process troubleshooting and furnace tap hole monitoring solutions was also implemented at one of the world's largest fully integrated zinc and lead smelting refining complexes in Canada. The system provided value by giving an indication to engineers and operators as to the integrity of all the tapping blocks of the furnace and when they may potentially become unsafe to use. The ore beneficiary process at diamond mines could be described as a complex and expensive balancing act where flow rate, size, density, and other factors must all be in balance if any degree of plant optimization and efficiency is to be achieved. This requires not only complex models, but uninterrupted real-time measurement of such key parameters as material flow rate and density, especially in the event of sensor failure and even when there are no sensors available. With AI-driven soft sensor technology that provides a digital twin of a hardware sensor, a solution was provided to not only measure more accurately, but to identify sensor failure in real time and provide sensor values as derived from other sensors to generate the simulated sensor values. A Dutch zinc manufacturer of rolled titanium for applications in wall cladding, gutters, roofing, and rainwater drainage systems was confronted with inconsistent product quality, resulting in expensive rework and metallurgical properties that changed without any obvious reason. With a machine learning-based solution, it was possible to reduce the production of defect products and to reduce the rework and reprocessing, which directly led to improved efficiency and lower production costs. As the solution also provides detailed causal analysis, sensitivity analysis, and what-if scenario analysis, the zinc manufacturing process engineers were able to better understand the intricacies of their production process and to continuously improve it. The efficiency of the electrowinning process, which recovered metals from electroplating rinse waters at a Belgium precious metals refining plant, needed to be improved in the face of challenges that would force the plant to figure out new ways of dealing with change. An AI-enabled solution was implemented that not only increased the efficiency to 94%, but also helped to map the threshold values for impurities, which led to an improved strategy for bleeding electrolyte from the plant's electrowinning circuit. In addition, some new process insights contributed to further annual savings due to the removal of costly corrective actions, which did not produce an evidence-based positive impact. An aluminium smelter in Australia had unacceptably high variation with their green anode density in their batch mixing paste plants. Machine learning models were deployed that resulted in specific process improvement recommendations that led to the reduction in anode quality variation. At an alumina plant in Western Australia, a real-time causal analysis solution was implemented that resulted in the causticizer unit, which makes caustic soda by controlling chemical reactions of soda ash and milk of lime in a dissolving tank and a reactor of the refinery, to be more proactive and consistent in its response to process deviations. From a business outcome perspective, the AI solution resulted in improved process stability, production rates, and product quality. An integrated steel plant in the Netherlands could not explain frequent breakouts at the continuous caster in their direct strip products section of their plant, where a single breakout causes hours of downtime at huge opportunity cost. An AI solution was implemented that provided early detection of potential breakouts and helped to explain other caster-related problems. At a very modern chrome chemical production plant in South Africa, ore is processed to yield sodium dichromate and chromic acid, which is used in manufacturing applications such as leather tanning and corrosion control. For example, in electroplating, metal surfaces are finished with a thin layer of chromium either for decorative purposes or to obtain a corrosion-resistant surface. A machine learning-based solution was developed for this plant to provide real-time mass balance calculations and an intelligent control algorithm to help stabilize the chromic acid crystallizer, and resulted in significant process stability with reduced variance, where the product was increased with 20%, drastic reduction in impurities, and greater than 50% reduction in plant downtime. At a world-leading heavy mineral sand extraction and refining plant in South Africa, rapid process troubleshooting and advanced process control solutions were implemented on both rutile and zircon circuits, with resultant financial and business benefits of 5% increase in product yield whilst maintaining grade constraints, as well as achieving a reduced product grade variation overall. A zinc smelter in the Netherlands needed to rapidly improve temperature control of their zinc roasters in order to maximize plant throughput. A real-time AI-based optimization solution was implemented that incorporated plant expert knowledge and experience to continuously improve the operation of their roasters and the rollout of machine learning-based rapid process troubleshooting to other plant sections. One of the world's largest ferrochrome producers in South Africa that produces charged chrome through a direct current electric arc furnace and metal recovery plant had a significant bottleneck in their dryer section where chromite ore needs to be dried before being fed to the direct current furnace. With rapid process troubleshooting that helps to understand the causes of variation and the implementation of an advanced process control solution, the variation on the dryer's baghouse temperature was significantly reduced, with throughput through the dryer that has increased by more than 35%, and no more damages to the baghouse filter bags due to temperature knocks were reported. In a discrete manufacturing process troubleshooting use case, specific causes for variation were also identified using a machine learning-based solution for an aluminium rolling plant in South Africa that experienced unacceptable reject rates due to offsets on plates being hot rolled. At a large aluminium die casting manufacturing in the USA that also, amongst others, provided parts for Harley-Davidson, AI-based process troubleshooting is used to identify and understand causes of variation of surface defects such as blisters and scratches that allow them to provide better quality product to their customers. At a global microelectronics manufacturer in the US that is a supplier of consumable materials such as chemical mechanical planarization polishing slurries to the semiconductor industry, one of the AI use cases involved mixer batch phase analysis, where mixer product temperature and motor amps were some of the key performance indicators that were modeled and analyzed. By modeling the ideal or so-called golden batches, anomaly detection and causal analysis can be performed to understand the contributing factors for batches that deviate away from the golden batches. Similar discrete and process troubleshooting and predictive analytics were done for semiconductor companies in the USA and Germany. For an automotive customer in the USA, AI-based solutions were implemented to assist with paint shop quality management with respect to reducing variation in key performance indicators such as paint quality index, reducing variation in samples from color to color between production lines and as a result of different processing conditions, yield, and concentration levels. The solutions also provided causes for paint shop quality problems, such as products that have poor process capability, many defects, and quality parameters that are out of control. One of the global leaders in the brewing industry wanted to improve their beer quality, reduce waste, and improve product consistency. An AI-driven solution was developed using the C-Sense software to troubleshoot and help to optimize limited extract, which is one of the key quality parameters used in quality control in the production of beers. One of the causes for variation in limited extract value were identified by causal and sensitivity analysis applied to the beer quality machine learning-based models. Optimal set points were determined for these manipulated variables to reduce extract losses and waste and obtain the best quality beer for each brand. Machine learning-driven solutions can also help engineering teams to improve their productivity and efficiency with respect to more efficient designs, quicker turnaround time, and eliminating waste in the design process. Motivo Incorporated, for example, uses AI to help fabless design companies to improve their yield and optimize their designs at reduced costs, better reliability, and faster time to market. Intel has also claimed that they have achieved a 10% higher yield for their integrated circuit products compared to other similar designs at a similar pre-production development stage. McKinsey & Company's MGI referenced a use case where a semiconductor manufacturer reduced its material delivery time by 30% and increased its production yield by 3 to 5% using machine learning-based approaches. MGI also mentions use cases where an aerospace manufacturer reduced its development cost almost 200 million euros with the development of AI-based productive tools for their engineering teams and saved 350 million euros by reducing unnecessary interruptions on the assembly line. An AI-driven, fully digitized supply chain can help to do real-time optimization of inventories, balancing of the supply chain, and visibility on supplier machine performance, availability, and downtime. AI can also help to provide better accountability throughout the supply chain, which can, for example, help aerospace and automobile manufacturing to better adhere to safety regulations. It can assist with making program review processes more efficient, addressing potential bottlenecks with respect to process, material, and staff in a preventative manner. Uptake is, for example, using AI and IoT to transform aircraft maintenance by deploying sensor networks for monitoring aircraft engines using machine learning-driven anomaly detection that analyzes the sound of airplane turbines, their operations, and predictive maintenance. By predicting maintenance, repair, and overall related work in an accurate fashion, one company reported profit increases of around 300 million euros through the use of AI to forecast 10 years of repair events for a fleet of 17,000 commercial aircraft. MGI reckons that aircraft maintenance automation can generate between $5 to $15 billion in annual business value for the industry through performance gains and labor replacement. When I was at General Electric, I remember them making use of the Kaggle data science competition platform to assist with the flight planning route optimization problem, where machine learning was used to optimize fuel consumption by incorporating inputs such as airspace constraints, wind, and weather patterns. The winning solution demonstrated a 12% efficiency improvement compared to actual flight data. Although there has still been a low adoption of AI in the construction sector, some relevant use cases for deploying AI solutions in this sector includes smart buildings and homes, agricultural and generative design assistance, automating the creation of building information model elements, managing parameters and interoperating with other applications, data sources, and geometry tools, improving building energy management and estimating energy performance of residential buildings, raising efficiency of air conditioning systems in commercial buildings, real-time equipment monitoring, diagnostics, anomaly detection, and predictive maintenance, autonomous equipment, and intelligent virtual construction assistants and advisors. Smart buildings involve the use of AI, Internet of Things, and smart sensors attached to buildings to increase safety by reducing risks such as flooding or fire, while also to reduce operational costs and improve energy efficiency through capabilities such as monitoring the movement of people around the building and adjusting temperatures accordingly. From a risk management perspective, insurance companies are incentivized to work with construction companies and large enterprises to create smart buildings and reduce the insurance premiums for companies that deploy such smart technology-driven solutions. Similar to the benefits achievable in smart office or public buildings, smart sensors in homes can at the same time enhance the household experience through optimizing climate control according to personal preferences, improving energy efficiency, and reduce operational costs by learning the electrical signatures of home appliances to switch heating and air conditioning on or off at the right times to exploit off-peak rates, or alerting consumers to optimum usage of washing machines or dryer, increasing safety by reducing risks like flooding or fire, reducing home insurance costs, and provide healthcare assistance by, for example, protecting the well-being of people with asthma through carrying out real-time pollen and pollution calculations.